Respected chairs, dear colleagues, ladies and gentlemen. Thank you, organizers, to give me opportunity to present part of our efforts to improve everyday clinical practice in field of radionuclide therapy. What is radionuclide therapy is a well-known method for treatment with different diseases. But it is always is compromise between wanted therapeutic effect on target tissue and unwanted damage of other tissues or organs, such as symbolically presented on this picture of the right side. We have to be according to two basic principles, primum non nocere and alara, during using of radiopharmaceutical or radionuclide therapy. Following the application of high doses of radionuclide therapy, usually patient must be hospitalized for certain amount of time until radiation in their body drops below certain level proposed by law. Usually, this period lasts 2 to 5 days and depends on different factors, primary amount of applied radionuclides and volume of target tissue. Some other conditions, such as kidney function and medication, also can influence on biokinetics and biodistribution of used radionuclides. A level of 400 megabecquerels, according to Serbian law rules, is a level when we can release patient to home from hospital. But this level is different in different countries. As example, in United States of America, this level is much greater. It is 1.11 gigabecquerels, about 3 folds greater than in Serbia. During this period of hospitalization, medical personnel can be faced with some challenges, surprises, and dangerous situations for both for patients and for personnel. First group of challenges are related to radionuclide therapy and its complications and comorbidities, such as radiation thyroiditis, radiation gastroesophagitis, sialoadenitis. In case of we use radionuclide therapy for treatment of differentiated thyroid carcinomas, and diarrhea, vomitus, psychiatric or neurological instability. In case of we use radiopeptides for treatment neuroendocrine tumors. Also we can face with cardiovascular changes in those patients related to changes of heart rate and blood pressure. In some of those cases, audiovisual contact with patients and follow-up of their vital functions with bedside monitor can be of high usefulness. In case of patient needs urgent intervention, it can ensure that nurse or physician can be able to do it on time, enough fast to prevent critical complications and fatal, in some cases, complications in these patients. Second group of challenges are related to limited capacities of dedicated premises for this kind of therapy and overall cost of this kind of medical treatment in the other hand. It is of high importance to estimate as early as possible the time period after which the radiation in the patient body will drop below the limit imposed by law. I said it is for iodine 131 in Serbia is below 400 megabecquerels. There are two crucial questions: when it will happen and how we can estimate it. Usually, we can estimate it by follow-up decline of radiation of exposure rate from patient body during hospitalization, usually using handheld monitor or survey meter to estimate actual exposure rate from patient body at a distance of usually 1 meter. But it is dangerous for operator, for physician, for physician, or for nurse, because of high level of radiation gets their body during this measure. Also, it is uncomfortable because of it must be finished few times during hospitalization, few tens of times during whole hospitalization to be sure is radiation in patient body enough low to we can release patients to home. Third group of challenges are related to unexpected behavior of some patients who sometimes try to leave restricted area despite strict instructions given before administration of radionuclide therapy. Because of human reasons, we cannot use locked doors or wire barriers in this case. We need a specific alarm system which is able to announce personnel when such case occurs. Based on our previous experience, we decided to use telemedicine approach to resolve those challenges. This article published in this newspaper 90 years ago announced nowadays reality, but it was science fiction in this moment when it has been published. Using our experience, we have developed comprehensive telemedicine system which is able to answer to all previous mentioned challenges. This system consists of own developed hardware and software modules which are accessible remotely by some kind of remote access connection, such as virtual private network, remote desktop connection, virtual network computing, or most popular, TeamViewer. First challenge was estimation online audio-visual contact with patients and follow-up of their vital functions to on time prevent adverse reactions and complications after radionuclide therapy. As solution, we developed a system for video surveillance of area which use patient, restricted area, which use patient during hospitalization, and continuous online remote monitoring of patients' vital functions registered with bedside monitor. Video surveillance of physical isolation area is conducted by two IP cameras set either to computer view or to mobile phone view with different frame rates and different resolution. Remote monitoring of vital functions is conducted by Nikon Holden bedside patient monitor equipped with appropriate network card and appropriate software, which enables that physician can watch at personal computer, at home or in office, or on mobile phone, mobile phone, all waves and vital sign patterns from bedside monitor, which are distributed via network, and also live video from surveillance cameras during patient hospitalization. Few years ago, we have published one paper in prestigious Telemedicine and e-Health journal dedicated for telemedical applications. This paper has been dedicated to this model. Second challenge, and I think most important challenge in our realization, is how estimate as early as possible level of 400 or different level for different radionuclides when patient could be released from hospital to home. We developed system for continuous online remote monitoring of rescue activity in patient's body, online in real time, using one probe copied this model, which is connected to pan-tilt zoom device and a digital video recorder, which enables precise positioning of detector on target region of patient's body because of we need consistent geometry during a measurement at a distance of 1 meter. The positioning of the detector is visually controlled by a micro camera placed at the center of detector's plane. Furthermore, there are 3 laser pointers placed around the detector's plane. And we are able to control where is field of view of detector during this measurement. All is controlled by the DVR. In addition, we use 2 ultrasound sensors from car parking system Parkmatic to estimate is position proper from point of view of distance. Is this distance 1 meter or more? We can see on this picture live video from micro camera with 3 laser points on the patient chest, which indicate where is center of field of view of detector, and estimate distance from Parkmatic system of 1.25 meter in this case. We can correct it in any time via internet connection from everywhere. All data collected by probe we use for further analysis by Teramino group developed system as interface between probe and between personal computer, which is able to register actual count rate, count per minute or count per second from patient body, exposure rate from patient body in this moment. We can see numerically and graphically for longer period of acquisition. Using remote connection, physician can watch online radiation exposure rate in any time from any place and can use commands of pan-tilt zoom device and digital video recorder, to check is measuring position proper or not, and correct it. We can see on those pictures actual count rate from patient body and live video from micro camera. During whole hospitalization of patient, we can acquire more than 4,000 points, which represents exposure rate from patient body during whole hospitalization and during different activities of patients in a restricted area, such as sleeping, rest, movement, using showers. This graph shows those points as violet objects during whole period of hospitalization. But for further processing, we use reference points acquired in same geometry during hospitalization. During first 10 hours of hospitalization, those points are red on this picture. We can control position of measurement using micro camera, US sensors and laser pointers, and correct it using DVR and PTZ if it is need to correct. Our software use those reference points and mathematical model to estimate whole process of elimination of radioactivity from patient body using reference points acquired first day during 10 first hours after radionuclide therapy. It predicts, this yellow line is its function, it can predict when radiation in patient body will drop to defined level, before defined level of 400 megabecquerels as an example for 131 iodide. This prediction is good. This picture confirms this prediction is very good, and we published one paper related to this module a few years ago, also in this telemedicine and e-health prestigious journal. Third challenge is how announced medical personnel when patient try to leave an unauthorized leaving of restricted area. We developed alarm system dedicated for case when patient attempt to leave special restricted area active premises. Our system is over doors at the end of corridor which patient must use in this case when try to leave this area. This is schematically 2 apartments, corridor, and our alarm system over the door, slide door with the lid at the end of restricted area. Our system consists of survey meter equipped with pancake probe which is directed towards the corridor. Survey meter is connected to trigger circuit which gives signal in the case when the measured count rate exceeds previously adjusted value. Trigger circuit is connected to the programmable siren, blinking light, and alarm device unit which is able to call mobile or fixed phones. Also, it is connected to IP surveillance camera. On the siren, we previously recorded voice alarm such as attention, this premise, you should not leave, please return it, etc. In the case when the system is triggered, the patient will hear this message, see blinking light. Also, our system, Also, our system, when it's triggered, will call responsible physician and nurse on mobile phone. IP camera simultaneously records event and system sending via email appropriate data about it. 3 pictures as document who is responsible for alarming in each case, when it has been happened, etc. We will publish in Nuclear Technology and Radiation Protection one paper related to this module this year. Paper is accepted. We are waiting for publishing. We can conclude that we used our system for more than 500 patients who received radionuclide therapy. From our experience gained over the past 5 years, this comprehensive telemonitoring system dedicated for patients who received radionuclide therapy ensures high level of safety for all patients, medical staff, and population. Thank you for your attention. This is a picture of my hospital in my city. Thank you.